Welcome to the first exercise for the lecture Adaptive Filters. In this exercise, we will focus on the Wiener filter. We will have three sections in this video. In the first section, I will review some of the Wiener filter basics. Then I will have some comprehension questions for you so that we can dive more deeply into the topic. And in the final part, we will have two Python demos. The source material you'll receive will be for the second and third part. You will get a question set, also with the corresponding answers. Please make sure to look at the material before you watch the video, so you have a chance to work on the questions yourself. The same goes for the Python scripts you'll get. I'll walk you through the structure of the scripts, and you'll get the chance to actually implement some functionalities yourself before I then walk you through my implementation and discuss the results. So let's get started. Let me review the basics of the Wiener filter. I will do this using the noise reduction application. Within this application, we start with the signal S of n. And this signal is our source signal. In the lecture, it is very often a speech signal, but it doesn't have to be. The most fitting terminology is actually to simply call S of n the desired signal. The other signal we have is B of n, which is a noise signal, also referred to as the undesired signal. Important is that B of n is additive to S of n. Both signals together yield the signal Y of n. This signal is called the observable signal, meaning that whenever we want to observe our desired signal, we can only ever do so together with this noise signal in form of Y of n. And this fact motivates our filtering approach. We want to filter the observable signal, and I denote this here by giving FIR filter coefficients h. And we want to filter the observable signal in such a way that the output of the filter is a signal that is as close as possible to our desired signal. So the output should be an estimate of S of n, the head here denoting the estimate. So S head of n is an estimate of S of n. And to see how close we actually are with our estimate to the desired signal, we can look at the difference signal between the two signals. And the difference signal, E of n, is also very commonly called the error signal. The set of filter coefficients for a Wiener filter is derived using this error signal within a cost function. So the cost function of the Wiener filter is that the expectation of the squared error signal is minimized. So very important, this is the cost function of the Wiener filter. And if we can assume some signal properties, we can derive some optimal filter coefficients with respect to the given cost function. So we get a solution. And in the time domain, then our optimal filter coefficients h opt are given by RYY and the inverse of that times RYS at 0. And capital R is the autocorrelation matrix. And the lower R is the cross correlation, not matrix, but vector. And if we want to compute this in the frequency domain, we also have a solution there. then this breaks down to 1 minus SBB divided by SYY. And then the capital S is a power spectral density. With regard to the signal denoted in the index. So these are the basic solutions of the Wiener filter. In addition to this solution, the lecture introduces modifications catering to the needs of audio and speech processing applications. And the solution here is then that we take the maximum of two values. The first one is Hmin, and Hmin is a lower bound. And the second value we take then the maximum of is similar to our frequency domain solution up here. It's 1 minus, but we add an additional factor, k over. K over we call the overestimation factor. And then the rest is the common solution, SBB divided by SYY. And this K over, this overestimation factor puts an additional gain on our noise estimate. And we have to use some of these modifications because in real applications, we are forced to work with estimates also of our power spectral densities. And you will get more information on these modifications in the course of this exercise. So let's look at the significant processing steps we need to implement a Wiener filter processing chain. First, we need to apply an analysis filter bank to take us to the frequency domain. The simplest method is to use a DFT here. And the result is a discrete and complex short-time frequency spectrum. We also change from sample to frame processing here. The next step is to estimate the PSDs. For SYY, it is straightforward. We just take the magnitude square of the current short-time spectrum. And this is an instantaneous estimate. For SBB, it is a little trickier since the noise signal is not directly available. But both methods to estimate SBB that we showed you in the lecture, they make use of a recursive smoothing. So they are not instantaneous estimates. And they smooth the power spectra over time. And the first method is the VAD method. And the VAD method, it uses a voice activity detection algorithm which detects the presence of speech. So if the algorithm does not detect speech in the current frame, the frame is used to update the PSD estimate. During phases of speech, the PSD estimate is not updated at all. And the second method we showed you in the lecture was minimum tracking. And here, all frames are used in the recursive smoothing. However, based on a specific rule, two different time constants are applied, which allows for an update of SBB also during phases of speech. Once both PSDs they have been estimated, we have all the quantities to actually compute our Wiener filter weights. And there you just use the equation that I showed you earlier. Best would be to use the one with the maximum operator. And once we have those weights, we can apply them up here as a multiplication. We multiply them with our short-time frequency spectrum of our observed signal, and we still have our phase information there. And this multiplication is, of course, then frequency selective. The output of this multiplication is then a estimate of the desired signal short-time frequency spectrum. And then we still need to take this back to the time domain, so we need to apply our synthesis filter bank. Since we used a DFT in the analysis filter bank, we use an IDFT here, which should operate, for example, in overlap add mode. And there we have then the estimate of our desired signal in the time domain. This was the review of the Wiener filter basics. Now I will go into the comprehension question section In the course material, you received a set of question and answers, and here I selected only some of those questions, but I will give you a bit more detailed answers to those questions. The first question is, what problems occur when using the time domain solution? So for this, let me write down the time domain solution again. It was that hopt equals to ryy, the inverse of that, times rys at 0. And you see here that we require two different quantities. The autocorrelation matrix RYY, it can be computed easily. The inconvenience here is everything that comes along with the required matrix inversion, but that's not the problem I want to talk about here, it's just an inconvenience. The cross-correlation vector, however, is an actual problem, since for straightforward computation, access to the clean desired signal is necessary. See here we need the cross-correlation between the observed signal and the desired signal. But if we had access to that signal, to the desired signal, there would no longer be a point in applying a Wiener filter. So that time domain solution doesn't actually help us with the problem that we set. So how the time domain problem solve when using the frequency domain solution? Again, let me write down the solution. It's that hopt equals to 1 minus SBB divided by SYY. And you see that this solution also needs two quantities like the time domain solution. But for none of them, a matrix inversion is necessary, so we got rid of that one inconvenience. But you also see that neither of the quantities requires access to the desired signal. And for both the PSDs that we need here, there exist methods to estimate them. Consequently, the frequency domain solution is the better choice for practical applications because we don't need access to the desired signal and we have methods to estimate all the quantities that we need. What is musical noise and how does it occur? And how is it avoided? So let us first look at two plots from the lecture. In the upper plot we see three different quantities. In red is our observable signal y at a certain frequency band. So this is y. And since the noise is stationary, you can clearly see where speech is present, for example, here, here, and then we would say that here this is, for example, a noise phase. The black line is the short-term power of the observable signal, which corresponds to the estimate of SYY. So this is then SYY. And the blue line is a realistic estimate of SBB. So this is then sort of SBB. Now, if you remember the frequency domain solution, that was H equals to 1 minus SBB divided by SYY. You understand that the instantaneous relation between the black and the blue line, which is SBB and SYY, that instantaneous relation determines basically the Wiener filter weight. And the Wiener filter weight is the value that we see in the lower plot in form of the blue line here. For analyzing the behavior, we need to distinguish between the phases of speech and noise only, like I pointed out earlier. In speech phases, the behavior is good. The weight is close to 1 and it's relatively constant within this phase. In noise-only phases, here and here, the behavior is quite erratic actually, and the weight changes between low and high values quite often. And this erratic behavior is the direct cause for musical noise, since it leads to fast changes in the frequency content of the estimated signal, which is in turn perceived as a number of tones frequently switching on and off. To avoid such a behavior, we must ensure that the weight is relatively constant within the noise-only phases. And let's imagine a case where our SBB estimator is not working properly and produces an offset of, let's say, 12 dB. Then this would be the estimate we get. So this is then SBB plus 12 dB. And you see that this line is well above SYY in the noise phases, which then leads to the Wiener filter weight as given here in red in the lower plot. And although we estimated SBB incorrectly, the incorrect estimate leads to the desired temporal behavior of the Wiener filter. So we are still quite constant with high values in speech phases, and we have constantly low values in the noise-only phases. And since this incorrectness of the noise estimate should not be arbitrary, we can use the output of our correct estimator and always add a constant gain. And this is exactly what is achieved by the so-called overestimation factor K over, which is added in the frequency domain solution. So then our new filter weights are given by 1 minus K over times SBB divided by SYY. And this solution with the overestimation factor prevents basically musical noise. Why is the frequency domain solution extended by a maximum operator? So what does this extension look like? H equals to the result of a maximum operator, and the first parameter is H min, and the second is our frequency domain solution, very often with the overestimation factor, and we certainly have estimates of our PSDs there. So by using the maximum operator, we introduce a lower bound H min to the Wiener filter weights. Let us consider that we set H min to 0. So H min equals 0. Then what does this do? This basically prevents negative filter weights. And negative filter weights we might get due to estimation errors of our PSD estimates. And this very often happens in the cases when we want to prevent musical noise in combination with the overestimation factor. So by setting H min to 0, we counteract negative filter weights. And the second case we have is that we generally just set H min to any number greater than 0. And here, of course, we also prevent negative filter weights, but by setting a specific number here, we're defining the maximum attenuation that the Wiener filter can actually apply. And we want to do this because in some cases we might not want to cancel out the undesired signal completely. We want to keep some of the signal, or we don't want to cancel that out at some frequencies. We want to retain some of the information that was there with the undesired signal. Especially with phone calls, something like that, we still want to hear some of the environment that the call was recorded in, or something like that. So by setting this H min greater 0, we're just defining a lower bound for filter weights, which gives us basically a maximum attenuation of our Wiener filter. This completes the comprehension section, and we will now go into the Python demos. So let us start with the time domain demo. For the script, you require the packages as imported at the top. And then the first thing we do is we load two signals, both a speech and a noise file. By doing this, we can artificially create the observed signal. And as you can see, we simply add the weighted noise signal to the speech signal. And the weight is used so that we can steer the power of the added signal for demonstrational purposes. We also limit our analysis to the first 500 samples so that we can assume stationarity within the signal. The script is structured for computational steps. You need to start with computing the quantities required for the time domain solution, and those are namely the autocorrelation matrix and the cross-correlation vector. Since we're running in a demo here, you should make use of the fact that the desired signal is readily available when you compute those quantities. Having computed the two quantities, you can compute the optimal filter coefficients using the time domain solution. Once you have these coefficients, you can directly apply them to the observed signal. The last section of the script provides plots of the observed signal, the desired signal, and the estimate of the desired signal, so you can analyze the effects of the Wiener filter. Feel free to vary the weight of the noise signal between 0 and 1 to capture all aspects of the filter's behavior. If you want to try implementing this demo yourself, please pause this video, as I will now walk you through the implementation and will discuss the analysis. First, we need to compute the autocorrelation matrix. Of course, there are several ways to do this in Python. I will use the convolution function from NumPy. Since we will have to shorten the convolution output to 500 samples, we introduce the variable yCallLong, and this is simply the output of the NumPy convolution function. This function gets the observed signal as both the first and the second parameter. However, make sure to flip the second parameter according to the definition of the autocorrelation function. The last parameter makes sure that the convolution is of full length with n-1 samples. Of those samples, we want the second half, since the autocorrelation matrix just needs the non-negative lags. These samples we store in yCore. And now we have all the values to populate our autocorrelation matrix. Remember that the matrix is a tuplets matrix, so the easiest way to create the matrix is to call on the function tuplets. And there you have the autocorrelation matrix. Next up is the cross-correlation vector. The approach is similar here. We again use the convolution, but with the speech signal as a second input. Remember to also flip the speech signal, and we also only want the first 500 samples of the speech signal. And then by selecting the non-negative lags, we already have the vector we want. So let's compute the optimal filter coefficients. We need to perform a matrix multiplication, so we call on NumPy's matmul. The first element should be the inverse of the autocorrelation matrix, so we call on NumPy's inverse function. The second element is simply the cross-correlation vector. And that's it. This line of code gives you the optimal filter coefficients. Now the last step is applying the filter. This we also do using the convolution function. But this time we don't flip anything because we actually want to perform a regular convolution and not a correlation. And we take the first 500 samples of the output, and this then basically just completes our script, and we can go ahead and run it. You see that the plots are pretty much the same. This is expected with the weight we set. This is basically our checking that the filter doesn't do anything unexpected when there's barely any noise present. So let's bump up the noise power by setting the weight to 0.5. The first thing you should notice is that the speech signal and the observed signal now differ quite a bit. The second thing you should notice is that the estimate of the speech signal is closer to the true speech signal than to the observed signal, especially in the second half of the displayed signal, where the filter is able to work with a significant number of past samples. To check this trend, let us set the weight to 0.8. As expected, the impact of the noise is even stronger here, but because of the Wiener filter, we are still able to obtain a good estimate of the true speech signal. And with this observation, I want to conclude the time demonstration, and we'll go on to the frequency domain demo. So let us go over the structure of the frequency domain demo. For this script, you also need some packages, and the ones you need are imported up here. We first load two signals. These signals are different from the time domain demo. One signal is an observed signal with speech as the desired signal, and the other signal is the pure noise signal, which is also contained in the loaded observed signal. And the rest of the script goes through the basic steps of the frequency domain implementation of the Wiener filter. For this, we first set a few parameters. There are the FFT size and the frame shift of the analysis filter bank, and there are the lower bound of the filter weights and the overestimation factor for the noise PSD. With these parameters, we transform both loaded signals into the frequency domain, and the short time Fourier transform function produces a matrix of the spectra for each frame. We added some plots here which visualize the matrices as spectrograms. And once we are in the frequency domain, we can estimate the noise PSD. So let me scroll down here. This is the area where you actually can do your implementation. So since we are in a demo here, we can work directly with the short time Fourier transform of the loaded signal. And please assume stationarity when you do so. With the estimate of the noise PSD, you can calculate the optimal weights for each frame. Please do so using the advanced solution with both lower bound and overestimation. Afterwards, apply the weights to the observed signal. Both computation and application should be done within the prepared for loop. The final step is to transform the modified signal back to the time domain. For this, you should use the counterpart to the function we used as analysis filter bank. This function, if properly used, will perform the synthesis free of artifacts and with proper scaling. When you run the script, it will plot the observed and the estimated signal so you can analyze the effect. The estimated signal is also saved as a WAV file, so you can go ahead and listen to it. Also feel free to play around with the values of the overestimation factor and with the lower bound. Once again, if you want to try implementing this yourself, pause the video now, as I will now run you through the implementation. So let us jump to the estimation of the noise PSD. A method to estimate a PSD of a stationary signal is to average short-term power spectra over time. The power spectrum we get by first taking the absolute values and then the element-wise squares of the STFT matrix. This matrix we can average using the NumPy mean function. To make sure that we are averaging over time and not frequency, we specify the axis to be 1. Although you can do this at a later point, we already apply the overestimation factor here so we don't forget it. Moving into the for loop. To compute the filter weights, we need a maximum operator. We use the NumPy version here. The first parameter of the function is the linear version of the lower bound. The second parameter is our basic frequency domain solution, 1 minus element-wise division of SBB and SYY. SYY we still need to compute as the magnitude square of the short-time Fourier transform, so we apply the absolute value and the squaring operators. With this equation we update the weights in each frame. Consequently, we need to apply these weights to each frame as well. This is done by an element-wise multiplication of the weight factor with the short-time spectrum of the current frame. Now all frames have been modified and only the synthesis is left. We can simply copy the STFD command from above and add a leading I for the inverse, and we of course need to change the signal that we want to transform. And this completes then the script and we can run it. The first plot we see is the spectrogram of the observed signal. We see power at nearly all frequencies due to noise, but we can also recognize a common structure of a speech signal. If we look just at the noise signal, it looks like this. Now let us move on to the results. You see here in the blue the observed signal and in red the estimated signal. Especially in speech pause, you see that noise is significantly reduced. However, although it seems that way, it is not clear whether the speech is read less and better SNR is achieved. So let us decrease the lower bound of the weight so we can achieve a better attenuation of the noise. I do this by setting the maximum attenuation to 30 dB. When I run this again, we can clearly see that the Wiener filter impacts the noise signal more than the speech signal. So let us listen to the signals. First, the observed signal.
Mancher gibt sich viele Mühe mit dem lieben Federvieh. Einesteils der Eier wegen, welche diese Vögel legen. Zweitens, weil man dann und wann.
Now the signal estimated with 30 dB max attenuation.
Mancher gibt sich viele Mühe mit dem lieben Federvieh. Einesteils der Eier wegen, welche diese Vögel legen. Zweitens, weil man dann und wann.
We can clearly hear that the noise is reduced, but the speech is retained. However, the quality is impacted by musical noise. You hear these instationary artifacts, sometimes also described as splashing of water. But we learned that we can do something against that. Let us increase the overestimation factor. It was already set to 5, so now we set it to 10. When we run it, you see it is very similar to our last setup. However, in the noise only section it is maybe a little smoother. But let us listen. First the old setup with musical noise.
Mancher gibt sich viele Mühe mit dem lieben Federvieh. Einesteils der Eier wegen, welche diese Vögel legen. Zweitens, weil man dann und wann.
And now the newest parameterization.
Mancher gibt sich viele Mühe mit dem lieben Federvieh. Einesteils der Eier wegen, welche diese Vögel legen. Zweitens, weil man dann und wann.
You should hear that musical noise and other artifacts are significantly reduced, if even still present at all. So this completes our demo in which I showed you the basic frequency domain implementations and specifically also the effects of our two parameters, the maximum attenuation and the overestimation factor. That concludes this exercise video. Thank you for watching.